Hey guys, so in the last video we talked about the Schrödinger wave equation I get after solving this Schrödinger wave equation is the wave function, right, psi. But what I know if I have this psi? Well, if you have psi, actually you know everything about your quantum system. So in classical mechanics, we have this position as the most fundamental quantity. If you know the position, then you can take the time derivative of position, which will give you velocity, and if you take the second derivative of your position function, you will get your acceleration. You can calculate from here, you can calculate your force, and here you can calculate your momentum, and you literally have everything if you know the position of your particle, right? But what about in quantum system? So in quantum system, there is a thing of indeterminacy, or we might remember that we had this guy Noah Heisenberg, who said in his principle that the uncertainty, you can't measure both position and momentum accurately at the same time. And this is your Heisenberg's uncertainty principle, right? Now the question is that what about the position of the particle, where the particle is? Well, in quantum mechanics, we don't talk about where the particle is, we talk about the probabilities of finding the particle. So we had this guy named as Max Born, and he gave this statistical interpretation. He said that let PE be the event of finding the electron, or you say particle in a quantum system, in a region between point A and B at a particular time t is actually given as mod of the wave function squared dot dx. So this thing gives you the probability of the finding of your particle in a quantum system, and here this thing, the square of the wave function, is actually your probability density. This is your probability density. So for a second, if I plot a graph, say this is your wave function square and this is your x, right? And suppose your curve looks like something like this, then this region is between, say, A and B. So this area under this curve or in this region gives you the probability of finding your particle. Well, now the question arises, like, because in real life what I see is that a particle is there, right? If I'm sitting here and if I draw a number line, and there are point 1, 2, 3, 4, and 5. So if my particle is at 4, then it is at 4, right? This is a classical mechanics approach, but in quantum mechanics, my particle could be anywhere in this region, but there is a chance, right, it is found between this 2 and 3. Particle can be anywhere between 0 and 5, here 0 and 5, but the chance of finding the particle is most between the 2 and 3, which is the amazing aspect of quantum mechanics, right? So now let's talk about the indeterminacy of quantum systems. So there are different approaches, there are different theories which says that where the particle really is. So one are the realists. So there is approach of realists who says that particle is really somewhere, like particle is somewhere. And actually, if particle is somewhere and your theory is not able to tell you where exactly the particle is, then it is the deficiency, or you can say the you know, the indeterminacy or the flaw in your theory. So it's a flaw there. Sorry, let me erase it. So it means that there is a flaw in the theory. But that's not exactly true, because what my theory predicts is actually matching with my experimental results, and that is the biggest test for any theory. So if your theory match with your experiment, then your theory is right. Well, Einstein was one of the realists, right? And actually, realists are wrong for most of what we say, believe in the physicist community. And because the next type of belief, that is of orthodox, of those guys who are orthodox, believe that particle was nowhere. And now this sounds super silly. Particle was nowhere, you know. Now you might say that what a nonsense it is, because what I am seeing in the classical physics with my eyes, that there is a car, right, at a distance of 5 meters or 10 meters or whatever, right? But you know, in quantum system, we are saying that particle is actually nowhere. Well, yes, and this is called as the Copenhagen interpretation, which says that the action of measurement actually leads to the, you know, production of particle. Well, this actually sounds silly, and honestly speaking, till date I find it silly, but yeah, it's true. So what happens when actually you make a measurement? Till when you haven't made a measurement, your curve looks like something like this. And the time I make a measurement, alright, like highlighted there, after measurement, what happened is, this is my curve, and let's take the spike, and yes, so the spike in this region shows actually determinacy, that the particle is now located in this region. But very soon this, you know, disruption, or you know, the collapse will regain its original shape, and the particle will be localized in all over the space. So these were the two views, realists and the orthodox, what they say about the position of the particle, because position is the most fundamental thing. And now we know that most of the physics believe in the orthodox system. So we'll be taking orthodox system in our mind and moving ahead with the theory. But before moving ahead, as we have seen that it's actually the game of probability, so we'll be taking a quick review of probability in next lectures, and after that we will be moving on to the quantum mechanics more deeply. Thank you.